Hello students, this lecture is for exact differential equation of first order and its solution. But before that, let us see what do we mean by solution of a ordinary differential equation. Solution of a differential equation. By the word differential equation, of course, we shall mean ordinary differential equation. Any relation connecting the variables in a differential equation without involving derivatives or differentials which satisfy the given differential equation. The equation means differential equation. That is, from which the given differential equation can be formed is called a solution or a formal solution of the differential equation. So solution of a differential equation definition is written. Any relation connecting the variables in a differential equation without involving derivatives or differentials which satisfy the given differential equation means from which you can form the differential equation by differentiating, etc. And that is called a solution of the differential equation, or it is usually called formal solution. The solution of a differential equation in which the number of independent arbitrary constants is equal to the order of the differential equation is called the general solution or complete solution or complete primitive. If a differential equation is of first order, then the number of arbitrary constant in this solution is 1, and that solution is general solution. If the order of the differential equation is 2, second order differential equation, then the solution with two arbitrary constants, of course these two arbitrary constants should not be related, independent, then the solution will be called general solution, okay, or complete solution or complete primitive. Number of arbitrary constants in the solution equal to the order of the differential equation, then the solution is general. The solution obtained by giving particular values to the arbitrary constants in the general solution is called a particular solution. Arbitrary constants can take infinite number of values, any values. If we give particular values, that will be also a solution, and that solution is called a particular solution. Okay. Sometimes a differential equation possesses a solution without involving arbitrary constants, but it cannot be obtained from the general solution. Cannot be obtained from the general solution by assigning particular values to the arbitrary constants. Such a solution is called a singular solution. Sometimes a differential equation possesses a solution without arbitrary constants, but also it cannot be obtained from the general solution by giving particular values to the arbitrary constants, and such type of solution is called a singular solution. We shall see the example. For example, y equal to cos x plus c is arbitrary constant, is the general solution of the differential equation dy by dx plus sin x equal to 0. This is a first order differential equation dy by dx plus sin x equal to 0, and y equal to cos x plus 1 is a particular solution, because if we differentiate y equal to cos x plus c, what we get? Dy by dx equal to minus sin x, derivative of c is 0. So if we side change, we get dy by dx plus sin x 0. Means from this y equal to cos x plus c, we can form this differential equation. That's why this is the solution, and here it is first order, and here is one arbitrary constant. That's why this is general solution. Now if I take c equal to 1, c equal to 0, c equal to 2, c equal to minus 1, then also it is a solution. Here in particular I have taken c equal to 1, so y equal to cos x plus 1 is a particular solution. Okay. Similarly, y equal to c1 e to the power 2x plus c2 e to the power thrice x. c1, c2 are arbitrary constants. Is the general solution of the differential equation d square y by dx square minus 5 dy by dx plus 6y equal to 0. How it is obtained, we shall see later. And if I take c1 equal to 3, c2 equal to minus 5, then I get this. This is a particular solution of this differential equation. Here number of arbitrary constants 2 and order of the differential equation is 2. That's why this is general solution. And from this relation y equal to c1 e to the power 2x plus c2 e to the power 3x, we can form this differential equation. This type of example we have seen in class 12 also. Y equal to this given, show that this second order derivative relation is equal to 0. This type of problem we have done. Later we shall also see in coming chapters. Now another one, y equal to x plus c whole thing square is the general solution of the differential equation dy by dx square minus 4y equal to 0. If we differentiate y equal to c x plus c whole thing square, we shall get dy by dx equal to 2x plus c, twice x plus c. If I put here it will be 4x plus c square means 4y, and already there is a 4y, so 4y minus 4y0 means this relation satisfies this differential equation and it contains one arbitrary constant. That's why it is general solution. And also y equal to x square is a particular solution. If I differentiate this, dy by dx will be 2x. If we square it, 4x square. 4x square means 4y. So 4y minus 4y equal to 0. That means y equal to x square also satisfies this differential equation. So y equal to x square is a particular solution if c equal to 0. Okay. Now this particular solution is obtained by taking c equal to 0. Now if I take y equal to 0, then dy by dx 0. So 0 square minus 4 into 0. So y equal to 0 satisfies this differential equation. Therefore, y equal to 0 is a solution of this differential equation. Dy by dx minus 4 whole thing square minus 4y 0. But this solution y equal to 0 cannot be obtained from the general solution. Means here y equal to x plus c whole thing square is the general solution. Cannot be obtained from the general solution for any value of the arbitrary constant c. So it is a singular solution. Why? You may say that if I put x equal to minus c, then we are getting 0. But that means c equal to minus x. But c is an arbitrary constant. You cannot take c equal to minus x. You cannot take c equal to x. You have to take a constant. That's why y equal to 0 cannot be obtained from this general solution. But yet y equal to 0 is a solution. We see that. So this is a singular solution. Of course, it is a trivial one, obvious one. We shall see another example. Y square equal to 4ax, parabola, equation of parabola. This is a singular solution of the differential equation y equal to px plus a by p, where p means dy by dx, means y equal to x into dy by dx plus a by dy by dx. This is the differential equation, and its singular solution is y square equal to 4ax. And how it is singular solution, we shall see in the later chapters. Okay. Now, why we have told solution is generally called formal solution. Here I have written formal solution. That will be explained here. Consider the relation x square plus y square plus 25 equal to 0. This is a relation between x and y. Okay. Differentiating both sides with respect to x, we get twice x plus twice y into dy by dx equal to 0. Dy by dx equal to minus x by y. Side change, divide. Substituting this value of dy by dx in this differential equation, x plus y into dy by dx equal to 0. This is the differential equation, and put value of dy by dx is minus x by y here, minus x by y. You will get what? X plus y into minus x by y means y cancels, x minus x 0. That means we get 0. That means this relation number 1. From relation number 1, we have got this differential equation, or this relation number 1 satisfies the differential equation number 2. Okay. So this relation number 1 formally satisfies the differential equation number 2. Here also you can do just cross and side change. We are getting this. Still I have shown like that. Value of dy by dx obtained from number 1, substituting in this differential equation, we have got 0, means this relation satisfies the differential equation number 2, or differential equation number 2 can be obtained from the relation 1. Therefore, by our definition, relation number 1 is a solution of this differential equation 2. So formally it satisfies the differential equation 2, but from this we cannot conclude that the relation number 1 is an implicit solution of the differential equation number 2. Implicit function, all of we know, an equation will be given, and in terms of this mixing x and y, and from this we can consider that y is a function of x. Okay, that is implicit function. But here this implicit, we cannot say that 1 is an implicit solution of 2, because from 1, why? From this line number 1, you see y square equal to minus 25 minus x square. So y will be plus minus root over minus 25 minus x square. So that y becomes imaginary. For any real value of x, under root expression is negative. So y is imaginary for any real value of x. That is, the relation number 1 does not define any real function of x. By solution, generally we should mean real function. But here this relation does not define any real function of x. On any interval of R, any interval you can take, any value of x you take, y is never real. So we are not getting a real function from this relation. Although this relation, from this relation we can find the differential equation, we can form the differential equation number 2, means it is a solution. That's why we call it is a formal solution. There is no real function at all in this relation, but it satisfies the equation formally, so formal solution. which has the appearance of a solution. Looks like solution, that's why we call it formal solution, but actually we are not getting any function, real function. So usually by solution of a differential equation, we generally mean formal solution. Okay. Now the question may arise, under what condition the real solution will exist instead of this formal solution. So this is only a statement. We are stating basic existence and uniqueness theorem for first order ODE, ordinary differential equation. Consider the differential equation dy by dx equal to f of xy, function of x and y, such that f is a continuous function of x and y. F is a continuous function of x and y in some domain D. D is a subset of R square. R square means xy plane here. And the partial derivative del f by del y. We know what is partial derivative, already explained in the last class. Del f by del y is also continuous function of x and y in this domain D. And x naught comma y naught is a point in this domain D. Then there exists a solution yx. Yx means y is a function of x of the differential equation 1. Solution yx of the differential equation 1 means this differential equation defined in some interval x naught minus h comma x naught plus h, where h is sufficiently small so that these conditions are true, that satisfy the condition yx not equal to y naught. Means the solution takes the value y naught when x is equal to x naught. Okay, this is basic existence and uniqueness theorem, means a real solution will exist, but we shall only state it, we shall not use it. By the solution we shall mean only formal solution, okay, in our syllabus. Now we come to our first point of syllabus, first chapter of syllabus, exact differential equation of first order. Exact differential equation. A differential equation is said to be exact if it can be obtained from its primitive by direct differentiation only and without any further process of elimination or multiplication, etc. Here, although I have not mentioned any order, here our syllabus is for first order, so it will by a differential equation means here first order differential equation, but the definition is true for any order differential equation. A differential equation is said to be exact, exact differential equation if it can be obtained from its primitive, means the original relation whatever given. For example, this is the primitive, from this we have found the differential equation number 2, so that is primitive. Okay, so if it can be obtained from its primitive primary relation given by direct differentiation only and without any further process of elimination or multiplication, etc. Generally we form differential equation from a given relation by differentiating and then multiplying, subtracting, adding many things to eliminate the arbitrary constant. But here this elimination, multiplication, etc. are not necessary. Just by differentiation, if we get the differential equation from its primitive, then that differential equation is called an exact differential equation. It may be of any order. Now, for a first order separately, I can define it like that. A differential equation of first order of the form m dx plus n dy equal to 0. This is the general form of a first order differential equation. Is said to be exact, said to be an exact differential equation if there exists a function u of xy. U is a function of x and y such that m dx plus n dy, means left side of this differential equation, is equal to d of u. To tell differential, d of u. What is d of u? We know, we have discussed in the last partial derivative lecture. That is m dx plus n dy is a perfect or exact differential. Means d of u means differential of single function. It is dx, dy are different differentials. M dx plus n dy is a group of function into differential, function into differential. But if this can be expressed like differential of single function d of u, then this m dx plus n dy is called a perfect differential or exact differential. And in this case, this differential equation is called an exact differential equation of first order. Where what is mn? Here m and n are functions of x and y, may be constant in special case. For example, x dy plus y dx equal to 0, as if it is m dx and that is n dy, like that, is an exact differential equation, because if I take u equal to x into y, xy, it is a function of x and y, then du equal to, see, we have done in the first class total differential, del u by del x into dx plus del u by del y into dy. So del u by del x means here y, because u equal to x into y, derivative of u with respect to x is y and derivative of u with respect to y is x. So you have taken there, it is y dx, x dy. So this is du, means our x dy plus y dx becomes d of u, x dy plus y dx becomes d of u. So by definition, this differential equation is exact. Okay. Now, under what condition a differential equation will be exact, necessary and sufficient condition. This is the theorem. The necessary and sufficient condition that the differential equation m dx plus n dy equal to 0 to be exact is that del m by del y is equal to del n by del x. That is partial derivative of m with respect to y equal to partial derivative of n with respect to x, where m and n are functions of x and y. Now see, what is m? M is the coefficient of dx and n is the coefficient of dy. So we remember like that, coefficient of dx is differentiated with respect to y and coefficient of dy is differentiated with respect to x, like that. Del m by del y equal to del n by del x. Sometimes m and n may be interchanged, then we can do mistake. That's why we remember like that. Coefficient of dx to be differentiated partially with respect to y and coefficient of dy to be differentiated partially with respect to x. And if they are equal, then the differential equation is exact. This is necessary and sufficient condition. Okay. So let us prove it. Necessary part means if the differential equation is exact, then we must have this condition. So let m dx plus n dy equal to 0 is an exact differential equation where m and n are functions of x and y. It is an exact differential equation of first order. We have assumed m and n are functions of x and y. Now our aim is to prove del m by del y equal to del n by del x. Of course, one extra assumption is there. This m and n possess continuous first order partial derivatives. They should possess partial derivatives, and partial derivatives are also continuous. That we assume. Now, because we have assumed this is exact, so therefore there exists a function u of x y such that m dx plus n dy equal to du. This is our definition. Now what is du? Already we know it is del u by del x into dx plus del u by del y into dy. This is our definition, formula for du. Already we know. Now since x and y are independent variables for the function ux, whenever we say that u is a function of x and y, function of two variables, volume is a function of pressure and temperature, pressure and temperature are independent variables, like that. U is a function of x and y, so they are independent variables. So dx and dy, they are increments in x and y. Dx and dy, differentials of x and y, are also independent. And when a relation like this holds, equality like this holds, where this dx and dy are independent, what we do? The coefficients you can equate from both sides. Therefore, equating coefficients of dx and dy from both sides, because dx dy are independent, that is most important, we get m equal to, m is the coefficient of dx in the left side, and here del u by del x is the coefficient of dx in the right side. So m equal to del u by del x and n equal to del u by del y. Okay. Therefore, del m by del y means this is m equal to del u by del x. If I differentiate this m with respect to y, what I get? Del y of del u del x, and that is del square u by del y del x by your notation of second order partial derivative. But order of differentiation can be interchanged, so that's why it can be written as del square u by del x del y. Now this is del x of del u by del y, means del x of n, because del u by del y is n. See, so what we have proved? Del m by del y equal to del n by del x. Therefore, the condition is necessary, means when the equation is exact, differential equation m dx plus n dy is exact, we have proved del m by del y equal to del n by del x. So the condition is necessary. Now sufficient part means if del m by del y equal to del n by del x, then we have to prove that the differential equation is exact. So let m dx plus n dy equal to 0 is a differential equation where m and n are functions of x and y possessing continuous first order partial derivatives such that del m by del y equal to del n by del x, means this condition is assumed. Now our aim is to prove this differential equation is, number one, is exact, means m dx plus n dy equal to d of single function we have to take. So to prove the equation 1 is exact, let u equal to integration of m dx, integration of m with respect to x, and below what we have written y constant. Because m is a function of x and y, we cannot integrate m with respect to x unless we know about y. So here we are keeping y constant as if partial integral. Integration of m with respect to x keeping y constant. Suppose it is u. So u will be a function of x and y. Then del u by del x is m, because differential and integral cancel each other, reverse. They are reverse of one another. So del u by del x will be again m. Obviously, because u is the integral with respect to x. So if I differentiate del u by this u with respect to x, I shall get m again function. Okay. Now we have del n by del x equal to del m by del y. We have this result assumed. So del n by del x is del m by del y, but m what we have got? Del u by del x. Therefore value of m substituted here. It is del y of del u by del x, means del square u by del y del x, but it can be written as del square u by del x del y, changing the order of differentiation. Now it is del x of del u by del y. So del n by del x is equal to del x of del u by del y. Okay, now if we integrate this with respect to x, partial integral, we get left side will be n, right side will be del u by del y plus phi y. Why phi y? Phi y is a function of y alone and free from x, because in this integral, in this process of integration, we have integrated with respect to x, assuming y constant. So our plus constant, when we integrate, we give a plus c, arbitrary constant, but that constant may be y, maybe log y, maybe sin y, like that, means maybe any function of y. That's why you have written n equal to del u by del y plus phi y. All of you know. Okay, y is a function of phi y is a function of y alone, free from x. Therefore, m dx plus n dy, value of m we have got del u by del x. Now value of n we have got this. So m dx plus n dy is del u by del x dx, because value of m is del u by del x, and value of n is now here. So multiplied by dy means del u by del y dy plus phi y dy. Now this del u by del x dx plus del u by del y dy is d of u, we know. Total differential, already explained in the last class. Okay, and this phi y dy we can write as integral of phi y dy with a d in front, means differential of integral. Differential of integral of phi y means it is like phi y dy. Okay, so this is a single differential, means d of u plus integral of phi y with respect to y, integral of phi y with respect to y. Okay, so it is d of b, let us write, where b equal to that, means m dx plus n dy is a differential of single function. Therefore, m dx plus n dy is a perfect or exact differential, and that means the differential equation 1, m dx plus n dy equal to 0, is exact, because this is our definition. If m dx plus n dy can be written as d of u or d of b, here it is d of b, so it is an exact differential equation. Therefore, the condition is sufficient, means del m by del y equal to del n by del x is both necessary and sufficient. So you prove the result. Now, method of solution of this exact D equation, m dx plus n dy equal to 0 when it is exact. How to find the solution? First method, when m dx plus n dy equal to 0 is exact D equation, there exists a function uxy such that m dx plus n dy equal to du, means del u del x into dx plus del u by del y into dy. Therefore, so that del u by del x is m, del u by del y is n. Okay. Now, integrating this number 1 with respect to x, we get u equal to integration m dx, assuming y constant, partial integral plus phi y. Whatever we have seen in the sufficient part also, this we have done. Now, differentiating this line number 3 with respect to partially with respect to y, both sides, we shall get what? Del u by del y. Left side and right side, of course, in practical problem, we shall find a function and we can differentiate, and that will be phi dash y. Means, but del u by del y is what? N. See, del u by del y is n. So we shall use del u by del y equal to n. If we differentiate number 3 with respect to y, we shall get del u by del y in the left side. We shall use this equal to n, and then simplifying, we can find phi y. And then the solution will be given by of this D equation is given by uxy equal to c. Why? Because whenever m dx plus n dy equal to du, so this m dx plus n dy 0 will become what? Du equal to 0. It will be du equal to 0. Differential of single function equal to 0. Now, if we integrate it, what we shall get? U equal to c, means uxy equal to c. So this is the solution. That's why after finding u, value of u, phi y, after finding phi y, we know u. What is u? Therefore, solution is given by uxy equal to c or u equal to c. C is arbitrary constant. So this is the first method. Okay. Second method is the method inspection method. When m dx plus n dy equal to 0 is exact, by grouping the terms of this D equation, the LHS of this D equation can be expressed as a perfect differential, means D of single function. D of single function, or sometimes it may be expressed as a sum or difference also, maybe of two or more perfect differentials, and then integrating we get the required solution. This is easier, but sometimes grouping the terms also not so easy. We shall see in examples also. And for this second method, this 4 important results will be helpful. Y dx plus x dy equal to d of xy. Already we have seen this is d of xy. X dx plus y dy is half d of x square plus y square. Derivative of x square is twice x. Derivative of y square is twice y into dy by dx. That's why it is just half adjusted. We get this. Now x dy minus y dx by x square is d of y by x. Y dx minus x dy by y square is d of x by y. So in simple result, still I have proved this Roman 4. D dx of x by y, suppose in class 11-12 we know d dx of x by y u by b. So derivative will be y square y into derivative of numerator x ddx of x minus x into numerator into derivative of denominator dy by dx. So it is y ddx of x is 1 minus x dy by dx y square. Now it is ddx. So if we multiply both sides by dx, it will become differential, means it will be d of x by y, and here dx will come, here this dx, dy by dx into dx will be only dy. So it is y dx minus x dy by y square. So d of x by y is y dx minus x dy by y square. We have proved. Similarly, number 3 you can prove. These are very obvious. Okay. So these results we shall use directly. Remember these results. Y dx plus x dy is d of xy. You can find ddx of x into y, ddx of x into y, and cross etc. You will get the result. And here ddx of x square plus y square, if we find, it will be 2x dx plus 2y dy, obviously. Okay. So half adjusted. Now let us solve some problems. Example number 1. Show that the D equation, differential equation, mdx plus ndy form is exact and hence solve it. First example. Let us see detail. Given D equation is, means differential equation is this, and it is compared with mdx plus ndy equal to 0. Suppose this is mdx plus ndy equal to 0. So what is m? M is here coefficient of dx, 2x cube plus 4y. What is n? Coefficient of dy, 4x plus y minus 1. Now what is del m by del y? Del m by del y is derivative of this expression with respect to y, means x constant. So this is 0, only derivative of y with respect to y is 1, so 4. Now what is n? 4x plus y minus 1. Now differentiate this with respect to x, means here y constant, so this part derivative will be 0, only 4x, x derivative is 1, so 4. So what you have seen? Del m by del y equal to del n by del x, and that is our condition, necessary, sufficient. Therefore given differential equation is exact. Now we have to solve. So let us see first by grouping. Now this is our differential equation, 2x cube plus 4y dx plus 4x plus y minus 1 dy. Okay. Now 2x cube dx can be integrated, because this is function of x, this is dx with respect to x. 4y dx, and here is 4x dy. We are grouping it, 4y dx and 4x dy. So 4 common y dx plus x dy, and then y dy minus dy can be integrated. This part can be integrated, and here y dx plus x dy, we know this is d of xy. Y dx plus x dy is d of xy, means differential of single function. So 4 dxy. So you see, this is perfect differential, this is perfect differential, this is perfect differential. So we can integrate. So just giving integration symbol, when we integrate, we give a constant of integration to the right side, c. So it is x to the power 4 by 4, and it is integration of dxy, means dt, integration dt, integration 1 with respect to t, like that. So it will be only t, means here xy. Okay. And it is y square by 2, you know it. It is 1 dy, means only y integration. So this is the required solution. Now we have solved it by grouping method, inspection method, second method. Now if we want to solve it by first method, star is given here, come to the star. Alternative method means first method. Let u equal to integration of m with respect to x, keeping y constant. Below you write y const. So what is m? Below of m substituted. Keep y constant, assuming y constant, integrate it as if partial integral. So it is x to the power 4 by 4, and 4y is constant, so integration of 4y with respect to x is only x will be coming here, 4y dx, means it is x, plus c will be written as 5y, because we have assumed here y constant. So that constant of integration is 5y. It is a function of y alone. Okay. Now we differentiate this u with respect to y. This u, this line, if we differentiate with respect to y, del u by del y, right side will be, this is 0, partially with respect to y, we differentiate 0. Here it will be 4x only, because derivative of y with respect to y is 1, and 5y derivative with respect to y will be 5 dash y, because this is now single variable, we can use dash, 5 dash y. Okay. Now value of n is this, del u by del y is n. Why? Note that when mdx plus ndy 0 is exact, then mdx plus ndy equal to du, we know, and del u by del y is n, del u by del x is m. Already we have seen in the proof of the necessary sufficient part. So that's why del u by del y is n. N means here 4x plus y minus 1. So 4x cancels, 5 dash y is y minus 1. Function of y here, right side. So you can integrate, 5 dash y is y minus 1. So what is 5y? Just integrate y minus 1. So it is y square by 2 minus y, plus c we are not giving here, because we shall see. Therefore solution is given by u equal to constant. What is u? U is here x to the power 4 by 2 plus 4xy plus 5y, and 5y we have got y square by 2 minus y. So u is x square by x to the power 4 by 4, 4xy plus 5y was there, we have found y square by 2 minus 5y equal to constant. Here we have not given any constant, you can give, I am showing it in the note. 5 dash y is y minus 1. Okay. So if we integrate, we have to give a constant c1, say suppose c1. Therefore solution is given by, now we know already exact equation solution is u equal to constant. Instead of c, I have written here c2. Now put the value of u is x to the power 4 by 2 plus 4xy plus 5y, but here 5y is y square by 2 minus y plus c1, and there is a c2. Now side change, c2 minus c1, and this c2 minus c1 is c, let us take. So this c1 we may not add, final answer will be same. c2 minus c1 is arbitrary constant, so adjusting constant we can get. That's why I have not added c here. Okay, so anyway you can do both the ways shown. So two ways we have solved this exact differential equation. First we have tested del m by del y equal to del n by del x, and then we have grouped the terms and then integrated and got the answer. Or by the first method, normal general method, we have shown solved. Now example 2. Examine if the differential equation y sin 2x dx minus 1 plus y square plus cos square x dy equal to 0 is exact, and hence solve it. So this is our differential equation. Here m is coefficient of dx, y sin 2x, n is coefficient of dy with this minus sign also. So del m by del y, derivative of m y sin 2x with respect to y, derivative of y with respect to y is 1, sin 2x is constant, so this is del m by del y. And del n by del x, here 1 plus y constant, so 0. And cos square x derivative is, we know 2 cos x, this minus sign will remain here, 2 cos x into minus sin x. Cos square x derivative is 2 cos x into derivative of cos x. Derivative of cos x is minus sin x, all of you know. So it is 2 sin x cos x minus minus plus, so sin 2x. Trigonometry, we know formula. So what we have got? Del m by del y equal to del n by del x. Therefore given differential equation is exact. Now solution, let us group first. This is our differential equation. Now this sin 2x I have written 2 sin x cos x, y is there already, and cos square x dy we have written here, minus 1 plus y dy, minus 1 dy and minus y dy. These are easy, we can integrate. Dy integration, y dy you can integrate, no problem. That's why here is a mixture. Now this minus we have taken common, cos square x dy minus 2y sin x cos x dx, here minus taken. Okay, now see, this line I have written as y into 2 cos x into minus sin x dx, means I want to write this is the derivative of actually cos square x. You can see here d dx of y cos square x is what? Cos square x into dy by dx, u into v rule, product rule, plus y into d dx of cos square x. D dx of cos square x is 2 cos x into minus sin x. So d of y cos square x will be, dx is coming here, it will be cos square x dy minus 2 sin x cos x, means sin 2x dx. So this cos square x dy minus y sin 2x, cos square x dy minus y sin 2x, this part actually d of y cos square x, that detail I am showing here. So cos square x dy plus y 2 sin x, 2 cos x, make it sin minus sin x into dx. So this I have written as d of y cos square x from this line, d of y cos square x. If dx comes here, it will be cos square x dy, and it will be 2y 2 cos x minus sin x into dx. Is it not? So that I have written. Group of differential, this differentials, two differentials giving a single differential, y cos square x d of. Now you can integrate easily. Of course minus sign is there, right side 0, so minus sign out. Integrating we get y cos square x plus derivative of integration of dy cos square x is only y cos square x, integration of this dy will be only y, integration of y square will be y square by y square will be what? Sorry, this is y, so this square is not there, this square is not there. Integration of y, this is not there, only y dy, so y dy will be y square by 2. Okay, so which is required solution. Now this grouping sometimes may not be easy. Alternative method, general method, let us see. First method, u equal to integration m dx y constant. Okay, it is value of m substituted, and assuming y constant, integrate. Sin 2x integration is minus cos 2x in divided by 2, because 2x is there, that's for 1 by 2. Rule of integration, you know, sin 2x integration minus cos 2x with a half. Okay, plus 5y, because we have integrated with respect to x, y assuming constant, 5y is constant of integration. Now differentiate this with respect to y, del u by del y. So del u by del y, derivative of y with respect to y is 1, so minus half cos 2x, and 5y derivative is 5 dash y. Now del u by del y is n, we know, because it is an exact equation, and value of n is minus 1 plus y plus cos square x, and here cos 2x we have written trigonometry, 2 cos square x minus 1, simplified. Okay, now see, cancels, minus cos square x and cancels, so ultimately what we get, 5 dash y equal to minus y and minus 1, and this half will be here minus half, minus 1 minus half minus 3 by 2. So 5y is, this is 5 dash y. So if we integrate, we get 5y. 5y will be integration of y plus 3 by 2 dy, that is minus y square by 2 and 3 by 2 into y. Plus c1 we are not writing because finally we shall use c. Therefore u we have got. What is u? U here was minus y by 2 cos 2x plus 5y. So minus y by 2 y cos 2x plus 5y. 5y is here, we have got minus y square by 2 plus 3 by 2y. Therefore solution is given by u equal to constant. So this is u equal to constant, and then just changing sign and crossing, we have got the solution. Y cos 2x plus y square plus 3y plus 2c. This is the solution. And here the solution is in terms of cos square x. Okay, you can change this cos 2x as 2 cos square x minus 1, and you can simplify, and you will get the same answer again here. This answer you will get. Y square by 2 is here, na? Y cos square x. Yes. 2 cos square x minus 1, if we write and then simplify, we will get this. Second alternative method. This is duplicate of this method actually. What we have done previously, u equal to integration m dx y constant. And because m and n here appear symmetrically, so you can interchange the process. Here we have written u equal to integration of n dy x constant. M dx y constant, here n dy x constant. Okay, so value of n substituted, integrating with respect to y, assuming x constant, we have got this line. Integration of 1 will be y, integration of y will be y square by 2, integration of cos square x means cos square x constant, so it will be only y cos square x with a minus n because of minus n, plus phi x. Why? Because we are assuming x constant here, and so answer constant may be phi x means maybe ax, maybe log x, maybe sin x, like that. That's why we have written phi x. In this process we have assumed x constant, that is why. Now we shall differentiate with respect to x, del u by del x. Del u by del x. So right side will be 0, 0. Here only cos square x derivative is 2 cos x bracket minus sin x. And phi x will be phi dash x. But del u by del x is m, because our differential equation is exact. Del u by del x is m. Del u by del y is n. That is to be remembered. Now put the value of m. And here it is 2 sin x cos x minus minus plus, so it is sin 2x. So m is sin 2x. So sin 2x cancels, y sin 2x cancels, so phi dash x is 0. Therefore phi x equal to constant, means c1 you can say. Therefore u equal to minus y square by 2 minus y cos square x, and here phi x is constant, c1. Therefore solution is given by, this time we are to bound to write u equal to c2, and then changing this c1 to right side, we shall get c2 minus c1 and 3 say, and then multiplied by 2 and cross, we have got this. And here 2 cos square x, we can write 2 cos square x as 1 plus cos 2x trigonometry, and then simplifying we get y cos 2x, y square, 2y and y, 3y plus 2c0. See this result, this answer and this answer exactly same. So these are actually similar method, duplicate of one another. And here if we write 2 cos square x minus 1 and simplify, we shall get this previous solution by grouping method, whatever we have got. Or you can multiply it by 2, 2y cos square x. 2 cos square x is 1 plus cos 2x, means cos 2x, 1 plus cos 2, so 1y, and this 1y will make it this will be 2y if you cross it, 2y, and there is 2 cos square x, that will be 1 plus cos 2x, means y, 2y, 3y will be coming, y square will be there, and y cos 2x plus c means this answer we shall get. Okay, so same problem we have done in 3 different ways. Okay, now let us see example number 3. Show that the D equation x dx plus y dy plus x dy minus y dx by x square plus y square equal to 0 is exact, and hence solve it. Our chapter is exact, so we have to check whether exact or not and to solve. So this is not in m dx plus n dy form. So you have taken the coefficient common, dx coefficient is x, here dx coefficient is minus y by x square plus y square. So this is coefficient of dx. Similarly coefficient of dy collected. So it is now m dx plus n dy form. So this is m, this is n. Now del m by del y. This x is constant, so 0. And del m by del y, because when we differentiate partially with respect to y, x constant. So it is y by x square plus y square, u by b. So it is b square, b into derivative of u means numerator 1, derivative of y with respect to y is 1, minus y remains, derivative of x square plus y square with respect to y is 2y. So you have got y square minus x square by x square plus y square whole square. Similarly del n by del x, y is constant because we are differentiating with respect to x 0, and this is again u by b we have applied, we have got this. So they are saying means del m by del y equal to del n by del x. Therefore, given D equation is exact. Now we have to solve. By inspection we are solving. Say x dx plus y dy, no problem. We can integrate it. You can integrate it here, only a problem. So what we have done, we have divided numerator denominator by x square. So this is x dy minus y dx by x square, means it is d of y by x. Already we have seen this, and the denominator is 1 plus y by x square. Okay, now if we integrate, we can integrate it because dt by 1 plus t square, like that. So it is x square by 2, it is y square by 2, it is tan inverse t, all of you know, but here t is y by x. So directly we have written this is the answer, which is the general solution, required solution by inspection. Done. Other way you can do. Now 2 homeworks given, show that the D equation this is exact and solve it. Answer is given. These two you will do. Thank you for today. More problems we shall do in the tutorial class or in next lecture class also.